do that kind of thing. So I think we are recording. Now, the results of the first test are up there. I would like to go through the test, but I want you guys to take time to go through the comments I make on your test. It's difficult to write on PDF files, so the stuff I write is not the best looking in the sense of drawing check marks for correct and X's for wrong. They're not the easiest things to write, but I also can't do exponents and I can't do logs, and I mean, I can't easily do square roots. I have to draw them, things like that. So it takes a long time to grade. So please look through those. We'll talk more about that later. I want to put on the screen something that we did yesterday class-wise, last class. When I try to read something off of when I'm talking and I see what might be a mistake, I suddenly panic and try to change things. On page 16 of your notes, and the people at home can see the screen now, on page 16 of those notes that I hope you all have around, it says class C2 real valued functions have equal mixed partial derivatives. That is true. However, the statement is not about class C2. Now, so basically the statement that I wrote is correct also. On Monday, I said, it looks like we should change that class C1 to C2. That was just because I suddenly thought I had made a mistake. I did make a mistake, but both statements, the heavy print, the heavy class C2 statement and the statement in the theorem are both true. Unfortunately, they are different. So I want to try to bring that up. What we should say is, what the theorem says is, I have a class C1 function on an open set. Now, what does that mean? That means the function, the partial derivatives with respect to the first variable, the partial derivatives with respect to the second variable, and however many variables we have, the partial derivative with respect to as many variables as we have, those are all continuous functions on the set U, whatever the domain is. So they're all nice and continuous functions. Okay, that's class C1. Now, what would class C2 be? It would be not only are all these things continuous, but in addition, all of the partial derivatives where you take the derivative of the derivatives, and this actually comes out to be lots of things, all of the partial derivatives that you have, depending on how many things go on here, all of these are also continuous functions. So if all the first order partial derivatives are continuous, and all the derivatives of the first order partial derivatives are continuous, that's class C2. Now, if you have a function of class C2, then the mixed partial derivatives are equal at a point. Now that means this one would be equal to this one, which I didn't list here. I guess I did list it, sorry. This would be equal to that. Okay, F13 would be equal to F31, F23 would be equal to F32. Those are the mixed partial derivatives. Nothing I really said the other day was wrong. It's just the statement is not about C2. This says if there's C2, then the mixed partial derivatives are equal. What does the theorem say? You only have to assume that you have a function of class C1 and the mixed ones are continuous. You don't have to assume, somebody want in? Yeah, thank you. I'll let them in with this here in just a second. Okay. So I need to get off this screen to admit people because I can't see the screen otherwise. Admit camera, admit John. Okay, thank you. So I'll go back to the share screen here. Okay, so as I said, the two things here. One, if the function is of class C2, all the mixed partials are equal. The conclusion is true. But we don't have to assume that this one is continuous and the F22 is continuous. In other words, we can still prove the theorem with less assumptions. So what unfortunately I did there was combine both things. There should be two theorems, okay? And this one, proposition 1418, once it's true, then a corollary of it is, well, if you also have all of them continuous, all the second order parts, then it's still true. That becomes an easy comment because all you're doing is adding more things that you've already verified. Okay, so I wanted to say that because in class, when I quickly looked at it, I thought I made a mistake. Well, I did make a mistake in a sense, but in the wrong way. Okay, so enough of that. For those of you just joining and stuff, what's on the board here are the wonderful grades that you all achieved. And the only solace, the only good thing about it is some of you might not feel so bad if you see that everybody else was below you. Now, some people will feel bad because they're not higher than other people, but you already felt bad anyway, so you're not feeling more bad. All right, maybe. Anyway, okay, so today I want to talk about the chain rule and what it gives us. And the book does examples in a certain way, does these problems in a certain way in chapter 14. And I want to show you other ways to do the same thing, so to speak, which sometimes is better. And I'm talking about section 5 in chapter 14, which starts on page 977. Now, the author makes several cases of the chain rule, depending on the dimensions of the functions involved. Now, I'm going to erase this numbers here so people at home can see the screen better. I'm hoping the yellow chalk has made some of the things I write better to see. I hope so. Anyway, okay, so suppose, now I'm going to write more. The author uses variables most of the time, and that's okay most of the time, but I want to try to show you what's going on with the chain rule. So if we have a function f and a function g, now in general, these are vector valued, so I put bars under them. And now, again, nobody else is waiting. I'm not going to worry so much about domains and ranges right now. It's the dimensions I want to worry about. When we define a function, you're supposed to know where you're talking about. All right? I'm going to just say it is a certain number of dimensions here. I don't want to say a set U and a set V and stuff. So I'm just going to declare this function to be some, now this is not the domain really, but that's just because I'm trying to emphasize something else. So what we have is two functions. We want to talk about a composition. When we talk about a composition, the composition starts somewhere. So I'm going to start here in n dimensions and go into m dimensions. And then this one's going to start in m dimensions and go into p dimensions. Now, technically speaking, we don't know that the functions are defined on all of this dimensions. They might be defined on a subset. I just don't want to take time to write 5 lines to say all that. Okay? So normally we define things that may be defined everywhere, may not be defined everywhere. But what I'm emphasizing right now is the dimensions. Okay? So we have the functions defined on a subset of m dimensional space. This one's defined on a subset of n dimensional space. Now, technically speaking, that means if I write G as actually m functions, F is actually P functions, because the number of functions that make up the vector valued function is the number of functions in the range. So if F goes into P dimensions, you're going to have P one-dimensional functions, and the same for G. Now, what's the composition then? The composition, again, this is not the domain, but just the amount of dimension. The composition is going to go from from N to P. The chain rule says, if I call this composition H, it says that if I make up the matrix of partial derivatives somewhere, and so I'm going to call the somewhere T naught, and T naught is a vector, is something that lives in the domain of G. The chain rule says that the matrix of partial derivatives is equal to the product of two matrices, namely the F matrix at G of T naught times the G matrix at T naught. So what we have is a whole bunch of partial derivatives. Now, this is good for all kinds of reasons. Sometimes we won't be doing exactly what I'm doing now, but other times I highly recommend you should do what we're doing now. The book does not do what I'm going to do next. And so what this should give you is additional stuff to do, partly when you get in trouble with notation. It's very easy to mix up the notation here, and what I'm going to do should clarify that. Also, from my standpoint, it keeps me from having to memorize a bunch of stuff. So, okay, what the book talks about on the first, he has a chain rule case 1, and what he says is suppose Z is a function of X and Y, he says. And suppose X is a function of T and Y is a function of T, different functions of T, okay? And he wants to make up a composition from this. So if we use variables, what would we do if we put these things together? We would say Z is F of G of T, H of T. That's how it might look. Okay? And then the question in the chain rule for the author is what is dz dt? Because if you would actually go and substitute, if you have a formula here that's written in terms of variables X and Y, and if you replace, every place you see X by the formula for the X in terms of T, and replace any place you see Y by H of T, and that'll be another formula, then what you'll get is a formula only in T. And if you go do that, you can just differentiate it because you've made a function of one variable. And so you don't ever have to use the chain rule in such a circumstance. You can just substitute, get one long thing in terms of T and differentiate it. What's the chain rule do? It enables you to figure out how to do that without sticking everything in. Because putting these things in might in itself be a big problem. Not a problem, but a big lengthy mess. Okay, so what we're doing, you guys have seen the idea of sometimes we use a chain rule, you recognize a composition, you differentiate the outside, leave the inside low. Anyway, it makes an easy way to do it. Okay, so now I'm going to do something here which goes along with this, and that is when I see something like this, I will draw a little thing where I combine the variables. Now the author does something like this also, but he also makes what I don't like to see, which we'll talk about in a minute. So what I like to do is to put the situation here, this is the F situation. What I'm saying here is Z depends on X and Y. the name of the dependence is f, if you want to think of it that way. And x and y, I've got myself, because of the space I'm limited to here, I'm kind of going off a little bit. X and y both depend on t. And the name of the function that is involved is g, and the name of the other function that's involved is h. Now, without memorizing, and also without doing what I want to do over here, I want to use the chain rule. If you use this kind of a setup for variables, then, and this can get us in trouble too, but the way to go to zz dt, this thing right here, is to follow all paths to get there. Now, each path is a partial derivative or a regular derivative. And so if you use this kind of thing to help you understand how to differentiate, there is a composite function here. But using variables, I'm avoiding these more complicated expressions over here. And by the way, later in more difficult examples, this stuff over here turns out to be simpler. Okay, but right now with this relatively easy situation, this is pretty simple. And what you do is you follow all paths. Now, if you have a path that has more than one variable here, you make partial derivatives, and we write that badly. I'm doing what the book does now. We write dz dx, that's a partial derivative of z with respect to x. That's that trail right there. You might see, instead of that, you might see df dx. We're going to see that sometimes when we don't have the variable z. Okay, so you might see this. This is just extra right now. dz dx and then dx dt. Now, why is one partial derivative and one straight derivative? Because this function only depends on one. You might see here dg dt, or you might see g prime. Plus, there's another way to get there, and that would be dz dy dt. If you see what I just did, and look in the book on page 978, you'll see I reproduced the formula that the author wrote. So, this little game we play with variables can get you the correct formula. Now, it is a dangerous thing to do, okay? Usually done by people who know less. And people who know less then sometimes don't know what to do with what they've got. For example, what's the second derivative? The second derivative, now I got to differentiate all that stuff. Well, we'll get to that. But that can be confusing. The other thing can be confusing is, suppose I want to talk about the derivative of this function at the number 1. Where do you put 1 over here? There's nothing in the notation that tells you where to put the 1, except when you guys learn, if I have the product of two functions, not these functions, but if I have the product of two functions at x, you all know that's f of x times g of x, if you have a product. So when you write something as a product and you evaluate it at the same place. That's what you do. So it would look like with this notation, if I evaluate the left-hand side at 1, then I need to evaluate the right-hand side at 1, which is true. But if you evaluate all 4 of these things at 1, you will be wrong. Because this one and this one are hiding the fact that they are compositions. These are functions of 2 variables. If you put 1 here, you're just making a dumb mistake, because you don't have, that function is not a function of 1 variable. So you'll put the 1 here and you'll put the 1 here, but here you will put G of 1 and H of 1, and here you'll put G of 1 and H of 1. So what's hiding this notation is good because you can quickly get a good formula, but it's bad notation because it doesn't tell you how to evaluate the formula. There's actually compositions in here. Remember when you differentiate composition, you differentiate the outside and leave the inside alone. And that's not 1, that's G and H of 1 in this case. Okay, now, suppose instead of that, and that's a good, nice thing to do, and we'll do it last. Instead of that, how would I interpret all that stuff if I have this kind of scenario? Well, the Z is, I have a function F and I have a function, I have a G and an H here and I have a G here. This is a vector G and this is not a vector G. So maybe I should change this to capital G right now so that we don't get confused with the letters. Of course, that messes you guys up because you can't just make changes like I do here so easily. So this is all be G's, capital like this. And so you look at all that and you say, G. Anyway, what is all going on here? Okay. Well, if I look at compositions, what I wrote over here someplace, this is a composition. And if I write variables just temporarily, this would be F of G of T, where G of T in this problem, G of T is, now, we can write them horizontally or vertically. Right now, because of my space, I'm writing it vertically. You can also write it horizontally if you want. It only matters when we start multiplying matrices together, okay? But it's a function of two functions, two of them. Since I wrote them vertically here, I would write them vertically here. Okay?
Dr. Brady,
Yeah.
can you give me a flow?
Thank you.
Dr. Brady.
Machines that Keegan's using. Keegan is not with us yet.
Dr. Brady.
He's joining. Okay.
Dr. Brady.
Okay, we don't. Oh, he's here. Hello, Keegan. Okay.
Dr. Brady, I think that's a question.
Yes. What? Somebody has a question? Who has?
Hi, sorry. So for the matrix that you just wrote vertically, the capital G of T, it's the top is the lowercase g of T, and what's the bottom? I can't really see it.
Oh, okay. Let me see if I can. In terms of trying to use the stuff I wrote at the beginning, the capital G now would be little g and little h. Okay.
So it's
Is that?
F.
Yes, thank you so much.
Capital G, because I've got two NOR functions here, and I'm calling those a vector function, capital G.
Okay.
Okay. So anyway, Z is F of, if I write this, instead of writing that, I would write F of G of T and H of T. Now I'm writing horizontally because I'm talking about a vector sort of thing now. This is the way we usually write this sort of thing. Anyway, this is what it would look like if I'm doing a composition. What's the chain rule say? Well, first, not instead of the Z, but I wrote H here. Now I've got to write capital H, okay? That's going to mess you guys up again. It's capital H because of little h over there. Okay, so capital H of T is F of G of T. Now, where does capital H start and where does it go in this scenario? The G starts with a T, that's one dimension. You take little g of t and little h of t, that's two dimensions. So what we have is we have a function that starts at one dimension, goes to two, and then f takes two things and goes back to one. F of x, y is z. Z is a number. So the case we're doing here in this first chain rule is going from one dimensions to two and then back to one. So what is the composition? It goes from one dimension to one dimension. Therefore, what is DH at T? Now, DH is a matrix of, well, H goes from, remember, n dimensions to P. But in this particular scenario, n and P are one. Now, this first case is so simple that you won't see how wonderful all this is because it all just breaks down. But later, if n is 50 and P is 47 and so on, and we got lots of different variables, this is a much easier way to do it. So if I'm just dealing with 1 and 2 and 1 here, I wouldn't do all of this. On the other hand, we will be doing other things and you need to do this. So bear with me. It will be like, yes, later. Right now it's like, why? But later, yes, I hope. Anyway, H goes from one dimension to one dimension. That's a 1 by 1 matrix. It's a 1 by 1 matrix of partial derivatives, but there's only one derivative, there's only one variable. What do we call that? A regular derivative. So all this is one thing. Now, if Z is H of T, I would call this H prime of T, or I might call it dz dt. And that goes along with what the author is trying to get us to do. Okay? And so it breaks down, instead of an n by p matrix, n is 1 and p is 1. So 1 by 1 matrix, that's just a regular number here, regular real valued function. What's the other side over here? It's df at g of t, times d, just a second, times dg at t. Now, what?
Should the H and the F be vectors?
Should, what?
Should, and DH, DF, that line that you just finished writing?
This one?
No, yeah. Should the F and the H be vectors and those?
This, I don't see anything I did wrong.
DH.
This, in this case, is just a little straight derivative.
Okay.
This is df of g of t times dg of t. Okay, we're going to see what that is in a second. F goes from 2 dimensions to 1, so it has 2 partial derivatives. This is f sub 1 at g of t and f sub 2 at g of t. It's a vector of, it's a gradient vector. It's got 2 partial derivatives, f sub x, f sub y, f sub 1, f sub 2. And the dg, it's a curve. When I differentiate a curve, how did you differentiate g? We had dg in this case becomes g prime, and that's just g prime h prime. So what we get is g prime here of t and h prime of t. So what you get this way with compositions is a row, a partial derivative of the function f with respect to the first variable, evaluated at g of t, partial with respect to the second variable, times the column g prime h prime. And when you put that together, and I guess I'll do it under here, when you put that together, what do you get? You get dz dt equals f sub 1 at g of t, capital G, times g prime of t plus f sub 2 at g of t times h prime of t. Now, I'm going to rewrite this up here without the circles so you can see it hopefully better. This was originally dz dx, dx dt, plus dz dy, dy dt. That's what we wrote earlier. What I want to do is compare these two. What is g prime of t? If I write up here, x is g of t, what do we call g prime of t? We call it dx dt in the other notation. This g prime of t and dx dt is what we call derivative of g with respect to t. What's it, dy dt? It's h prime of t. because y is h of t. So dy dt. So this and this are the same, and this are the same. How are they different? I am writing things here. I wrote this dx dz dt, but really it's h prime of t. You see the t when you write it correctly. What do you see differently here besides letters? You see all the t's in here. You see no t's in the numerator here. If I'm going to evaluate this at 1, I would evaluate this 1, and here is g of 1. G of 1 is g of 1 and h of 1, see? In other words, this notation tells you it's a composition. This notation does not. So the next thing I want to do is to write this without the t. If I write this without the t's, I've run out of room, so I've got it erased here. But if I write this without the t, what do I have? What I have is h prime in this particular case, because it's one variable. This is f sub 1 circle g times g prime plus f sub 2 circle g times h prime. When you erase the t's in a composition, it makes a circle. And so this is what you write when you take away the t. But when you do it properly, you see a composition here and here. When you have what I call bad notation, you never see the composition. If you don't see the composition and I want to differentiate again, you will make a mistake every time.
So if we had,
So if I'm going to differentiate this again, we're going to do that. And that's going to win, maybe right now. Anyway, if we do this again, let me just roughly show you, and I'm going to erase some of this, just because I don't have any room. You can look on the video, I guess, if the video comes up. Yeah.
would our sum be, it would be longer if we had more than 2?
Yes.
Okay.
Yeah. It's rows times columns. You have a 3 by or 5 wide, you'll have a 5 long.
Okay.
When you have more stuff. When you do a first derivative, you get compositions, but bad notation doesn't see it. Planes fall out of the sky. Anyway, if I were to differentiate that thing down there I circled again, I would do it easy first. Okay, you take the whole right-hand side and you say, hey, that's a sum. So I have f sub 1 circle g times g prime. I'm going to do that sub 1. What the heck? That's what, you know, I'm differentiating. I mean, this is all a function of t. And so when I say sub 1, really, I shouldn't say sub 1. What I should say in this problem is derivative. I'm differentiating that. And plus, I differentiate the other one, which is f2 circle g h prime prime in this problem. In more complicated situations, we might be doing subscripts. But since this is just you differentiate there, you differentiate the sum. This is a product. You have to do a product rule. So just playing games with symbols, this becomes the circle g prime. In other words, differentiate the first function, leave the second function alone, plus leave the first function alone, differentiate the second. That's doing half of it. Plus, okay, I'm running out of space that you guys can see on the screen here, at least big enough. The point is when I differentiate a product, I have a product rule. Twice now. I'm just not writing down the second part. You can write it out. Now, so that's fine. And in a second, we'll do it with bad notation to show you. The point here is the g prime, that's left alone. That was what the function was right there. And then we do, this is G double prime, that's okay. It's just a function of T. It's like T squared. You differentiate it twice and you get 2. So this is a product rule. Leave it alone, differentiate it. There's another one. What's the hard one? This one. Now, the cool thing for me, who's dumb, is I need to differentiate the composite. If I look around, what do I do over here? I need to differentiate a composite. Over here, the composite I need to differentiate was F circle G. Right? That's what I had to do. Now what I got to do? Now I have to do F1 circle G. It's the same thing. I mean, so what you do is take the answer to the first problem where I had to differentiate F circle. When I differentiate F circle G, I got this thing right here. If I differentiate F1 circle G, I will get this thing with a 1 wherever I saw F before. So in other words, this thing right here becomes F11 circle G, G prime, plus F12 circle G, H prime, times G prime. This thing becomes all of that. And that's where this way of doing things becomes easy. Because once you have the format for how you differentiate the composite in this situation, and you have to now differentiate another thing, you recognize, hey, it looks the same as the thing I just did. The thing I just did, I have a formula for. So how do I do the derivative of F1 circle G? I just put F1 wherever I had F in the other formula. Now I got to do it twice. I got to do it with the other half over here again. So in the end, what happens? You have 1, 2, 3. You end up with 6 things. Most people who do it wrong will end up with 4 things. And I've also seen this done in other non-mathematical places where some places always differentiate and get 4 things and they always think they're right and they've always been wrong, but they always do it the same way. And fortunately, they don't have to deal with real things where planes might fall out of the sky. Anyway, what goes on here, what I'm hoping to see is the value of this idea of compositions and using the form of the composition over again when you need to do this. Now, the thing we erased earlier, I'm going to go back and try to reproduce here somewhere. The thing we talked about earlier was we had a Z, we had an X and a Y, and we had a T. And we produced quickly with this little formula, dz dt equals dz dx, dx dt plus dz dy dt. Now, by the way, when I write fast, my d's look like 2's. This looks like 2y. My life, that's the way it is. I know it's a d delta thing, but sometimes people multiply by 2 now. Don't do it. This is means to be that way. I try not to do that, but I do it. See, I did nice here, but here I messed up. I had 4 of them to do, and I messed up 25% of them. Notation, that's common for me. Sorry, the way it is. I don't even care anymore. Now, how do I differentiate second derivative? Well, we can play games with notation. We do another derivative, right? D2z dt, this is how the second derivative notation is. What do you do over here? You would differentiate with respect to t, dz dx dx dt plus dz dy dt. Okay, ddt of that, it's a sum. Okay. I'm hoping you see it's the same thing. I had to do a sum derivative, so I had to differentiate the pieces. So the next thing you'll get is d dt of dz dx, dx dt plus straight d's, d dt of dz dy, dy dt, and I see that these should be straight y's here, dt. So that's the same thing as this top thing here, except you don't see any compositions. And then how do I differentiate the product? Well, how to do that? I said it was a product rule. So again, I have a product, so I'm going to differentiate, and I'm going to write it right here. The first one is going to be d dt of dz dx. Leave the other one alone, plus d dt, plus dz dx, d dt of dx dt. Now, d dt of dx dt is d2x over dt2. That's how we write second derivative. My question is, what is this? It's the derivative with respect to t of the partial derivative of z with respect to x. And here's where I am not smart enough to just know what to do. What's over here? The derivative of this. This thing right here is the d dt of dz dx. This thing here is that. But in this formation, I see a composition. It's the same form as the original problem I already solved. So all I got to do is copy the original formula with a 1 in front of the things I wrote. And then if I need to, so that's what this turns out. So what's this turn out to be? This stuff properly written, badly written. Namely, is F11 circle. So I've got to do the F11. How do I write that? That's the partial of F with respect to X twice times G1, that was dx dt, I guess, plus the partial of F with respect. Now, the next problem here is how do we write a partial thing? And books differ as to which one they write first and which one they write second. This sometimes is a problem of which they mean. Does this mean differentiate with respect to X and then Y, or does it mean the other way? Now, what is good about all of this? If the class C functions are class C2, the mixed partials are equal. If the mixed partials are equal, you don't care which it is, because they're equal. So it relieves us of having to worry about which way does a book mean. Okay, anyway, what have I left off here? This is times h prime, that's dy dt, and all of that has to be multiplied times dx dt to get this part here that was up there. Okay, so I grabbed this part out of there, right here. I grabbed it out of there. There's also a dx dt here. Anyway, I find it difficult to do this right here. I find this easy to do right here. And so when I'm doing second partial derivatives, I usually use this composition stuff because it shows me where the chain rule is involved. If you do this stuff here, you don't see where the chain rule is involved. I'm saying the notation doesn't help you see where the chain rule is involved. You got to be smarter. I'm not smarter. It's very easy to make mistakes in this stuff. So I like to have something I'm sure about before I just go. I can write all kinds of letters and variables and curly D's and straight D's all over the place, but have no idea what I'm talking about. Yes?
So I understand how we get to the point where we use F11 or F12.
Yeah, yeah.
but I'm not sure I understand where to get those values from. Like, it comes from the two-dimensional f function on the left,
Right,
but is that a 2 by 2
I
matrix?
understand. So all I can tell you at this moment is it will come out. We need to see more examples. I mean, what I did, unfortunately, is I erased stuff and stuff. There's no way I can read the tape back right now and maybe correct it for you. Just do more. I mean, the point is, one, if you go back over the video, that'll help. Hopefully I didn't make any mistakes, okay? But I want to do more here. We don't have that much time, only 16 after. It's only not only 16, it's too bad it's 16 after. What is case 2 in the book? What is case 2 in the book? Okay? These are the easy cases, by the way. Case 2 in the book is I have z is f of xy. Now, I'm just going to show you, it's easy to write. If you say z is f of xy, I write that down like that a lot of times, okay? And x is g of st. Uh-oh. So now I've got s is g of xt, and y is g of st also. So now I have a deal where both the functions x and y depend on two variables. We make this trail. Now, because of the time, at this second, I don't have time to do all this composition stuff, but look and see what you've got here. The composition, what I call capital H, that's z is a function of two variables. So capital H is going to be, now, when I try to do it, it's going to be two things because there's two partials. There's going to be a dz ds and a dz dt that I might calculate because it's from one, is a function of two variables. How do you write it down if you do it with variables like the book does? You say dz ds is dz dx. I follow all the trails that go to s. dz dx, dg, I'm sorry, yeah, dggs plus dz dy, dy ds. This would be the 1/2 of what you got to do now. Except sometimes they only ask you for a particular one. They only ask you for a particular one, you pick out the one you need to do. Okay? In this case, I just did the partial derivative of z with respect to s, and look, here it is. Now, how many compositions are hidden in here? 2 again. So if I were going to later do the second derivative of this with respect to s and then t, writing it that way, then now I got to do all of this with respect to things that have more partials. You understand? So because of the time,
Would the derivatives with respect to s, would those be regular derivatives?
I can't understand.
Would the derivatives with respect to s, would those be regular derivatives, or are they still partials?
No, these are all partials.
Okay.
Okay, and but it's my opinion that beginners can get confused with what to do. Not so much this, you can play this little game with notation just by following this pattern. But if I now ask you to do this on a test, I'll be grading for till December because people will have variables all over the place and all kinds and stuff and whatever. So the point is, what I'd like you guys to do is look at this chain rule, case 2, and try to put it into this form right here. On Friday, we'll talk about it. It's actually easy once you get understanding of what you have to do. Okay? The nice thing is we do the same thing every time. Look at how messy all this looks, but you do it slowly, and if you have a procedure, it will work every time fine. And now, what we haven't done, I've been doing this in general. Suppose you knew that, let's say, z is x squared plus y squared, and g, you know, and x is 2s, and y is the sine of t or something. If you know what these things are, sometimes you can just do it directly without having to go into all this routine. But other times, basically, you just quickly do this in general, see what I got, and I go up here and just say, okay, I need dz dx, that's 2x. I need dz, I need dx, d, you know, I need some, and you see what these are, you know what the format is in general, and you use those and you just replace these easily. Okay, so I recommend you get the general format every time, and then in particular cases where you're given nice easy functions, you can just substitute stuff. Now, in the end, if you do that, if I said this is 2x, I'm not supposed to put 2, this is now 2, TWO, not a partial. If I now say 2x, it's not supposed to be x, because it's a composite here. So I put 2x, but then I got to write, oh, x is 2s, and I got to put 2s in here. So if you start substituting stuff, remember that 2 of these things in this case are both composites, and we're talking about a function of s and t, not a function of x and y. So you don't want to have any x's and y's in your answer. You only want to have s's and t's in your answer, you see? So you go one substitution to get to the x, and then you do the other substitution to get to the whatever the s and t are. So I know we're over time. This is hard to say because of all these little notations. Please try to do this thing. And the next page, by the way, is the one in general. And again, the author does not use matrices. The easy way to do this in general is to use matrices. All I need to know is how many rows and columns I have. They're all partial derivatives. And if I need to know a particular thing, I take a particular row times a particular column, and I've got that partial derivative. You don't have to memorize anything except the chain rule. Okay, so I'm going to put the